Try computer audio. All right, daily quiz for DiffyQ's up. This is what we talked about at the very end of class on Wednesday. So we have that the solution to Newton's law of cooling was this function right here. The temperature of the object over time, so capital T being the temperature of the object, was equal to the temperature of the environment plus some constant times e to the negative RT, where R was some positive value. What happens to the temperature of the object as time goes on, as T goes to infinity? Well, I mean, you can type it in, or there's a nice little symbol. What's up?
It's assuming that the temperature of the environment is constant.
Yes. Good question. And what we'll kind of get into today is when we're doing a lot of our modeling, especially in here, we want to make a lot of assumptions like that. If you have a varying room temperature, it's just going to make it more complicated. And then while you're passively listening to that, or passively listening while you're doing that, today I'm going to be, just because it's easier than having to wait for me to write out a bunch of stuff. And I know how sloppy my handwriting is. So if we do a lot of writing, it's probably not going to be 100% readable because I'm just going to get tired. So I went ahead and typed up a document for us that we're going to be going through. I'm going to show it up here and I'm going to be writing in it. You can take your own notes. I wanted to actually have printouts for y'all, but I still haven't got this laptop hooked up. After this class, I will hopefully have it hooked up, but I haven't got this laptop connected to our printer, so I haven't been able to print this semester. So that is why I'm telling you, if you want to go ahead and download it right now, you can. For some of those of you lucky and have the tablets, you probably download and start writing on it. The rest, my recommendation is like what you have right now, like your laptop notes or something, or you can follow along. And anytime I write something in, just try to remember that whenever you actually get access to a printed version of this, this is what you're supposed to write. It's not perfect. I know it's not perfect. But that's what I'm having to deal with today. All right, stop share. But you got like a minute, but I think based on the way most people are looking, answers are in. All right, I'm going to lock answers here in 5 seconds. And remember, wrong answer is better than no answer. 3, 2, 1. Locking. All right. So most people got it. Let me just bring up the problem. This function, T sub E is a constant. That was what was representing the temperature of the environment, E for environment in this case. Right? And I even try to give you, if you didn't even remember the discussion or don't feel like you really understand what this thing is modeling and how it's working in the real world, I even gave you a nice little mathematical definition here, so you can rely on your calculus to figure this out. Okay, so that's the great thing about being an applied mathematician. You have all these different avenues to work with. So I need to figure out what's happening as time goes on and on and on. It doesn't stop continuing. What is happening to the temperature of this object? Well, it's being governed by this equation, TE, so temperature of the environment, plus some constant times e to the negative RT. So just thinking this as a function, I take the limit as t goes to infinity. Temperature of the environment, we're assuming is constant, right? So is that going to change at all as time goes on?
No.
No, constants don't change. It stays the same. Then I have plus another constant times e to the negative RT. That's where the interesting stuff is happening. That is e to a negative exponent, and that exponent is going to infinity. So technically negative e to the negative infinity. Overall, where does that function go? Never goes negative. Exponential functions are always positive. It keeps getting closer and closer to your x-axis. It goes to 0. So as time goes on, that e to the negative RT term just keeps getting smaller and smaller and smaller and smaller, essentially going away, essentially becoming 0. So I take constant, multiply it by something that's essentially becoming 0. Overall, that part of the function essentially becomes 0. And the function becomes constant. And what is that constant?
No.
You said the temperature of the environment. So as time goes on, I take this nice little apple pie. I don't know why I go to apple pie, but apple pie out of the oven. I sit on the counter. If I just leave it sitting there, assuming it's not going to rot away, or some animal is going to take it, or some little brother or sister is going to try to stick their hands in it, and it just gets to sit there over and over time, then it's just going to become the same temperature as the room it's sitting.
How do you write some low flow subscript?
Like on a computer or something?
Yeah.
What's the number? Wait, can't. Where can I type? Shh, you can't see anything. All right, so beside the 0 where you have your dash, if you do shift in that same button, there's an underscore. And the easiest way to usually represent it is using the underscore. But if you just said temperature of the environment, TE even, like if you just typed in this because you didn't know how to do it, I at least know what you're trying to convey. So all good there. All right. Share an iPad screen. Oh, while I'm getting this up, keep an eye out on XYZ homework. I know it's been a moment since I've given you a homework here in DiffEQ because I think the last homework was due on Tuesday. Right, so I owe you another homework. And it'll be after we get through this stuff. Right, so you'll probably have 1 or 2 more. Hey, solve these equations, whether or not they be separable or linear, like what we had before. And then some problems with this, because especially mixture problems are kind of fun. So really differential equations has multiple parts. As mathematicians, we usually do focus on a part, which is finding the solutions to said differential equations, right? You can add on an initial condition. That's okay. It just makes an algebraic equation I have to solve for later, right? The fun part is doing all the calculus to figure out how I go from an equation with derivatives to just an equation for my solution, right? Integration by parts, use substitution. If you want to get really complicated, you could pull in some of your trig techniques, and then surface area revolution, go to polar coordinates if you want to, whatever. But that's not the only part of the modeling process which we use differential equations for. Okay, differential equations are beautiful because we can do these calculus techniques, we know what the outcome is going to be. Or if you get into what I do research-wise, you approximate instead, because there's plenty of models out there that you can't actually solve, or there's not a useful written form for the solution. So you can't plug it into a computer and then study the solution, so you approximate. Either way, what it allows you to do in practice is you can change parameters, so change values of constants, and see how that changes the entire thing. It's much cheaper to do that, run a computer program that'll take 10 minutes and see the results, versus asking and paying for someone to sit in a lab and just keep using pipettes to pour, a sample into 200 different solutions of a mixture. That's going to cost a lot of time, a lot of money, and there's a lot more room for error. So modeling is often used in place of just physical experiments to begin with. Okay. Also, what more often than not, the area that I'm trying to get into, computational fluid dynamics. So if you're thinking of building an aircraft, right? You don't want to, or even a boat, you don't want to try to build 15 different models and then test those 15 different models, see which one is best, works best, and then take that model and then have to build upon that, make small changes to it so you get your final product, right? That's just a waste of time, a lot of waste of money, and a lot of waste of resources. So even if it's not used to get you the exact answer, these models are often used to inform where to look for the exact answer, right? I can mathematically model those 15 boats or those 15 airplanes and then see which one's performing better, so that when you want to go actually build it, you build maybe only 2 or 3 instead of 15. So you save a lot of time, a lot of effort, and a lot of money. This is huge. It can be hard to implement, but it's much more worth it and much more less time consuming than actually building or running the experiments physically. Okay. So no matter what we do, no matter what the process you get involved in, there's always 3 parts. Okay. Construct, analyze, and then compare. Models that we build, these mathematical models, including something like the following object model, predator-prey model, are never going to be perfect, right? Think back to the predator-prey model that we had. You can go all the way up to the top. That was following object. And this is what was happening with it. We had our prey either had to be exactly at 600. Otherwise, it would either skyrocket, predator would never be able to eat enough of it, and it just keeps growing and growing and growing, or it just quickly drops to 0. And in fact, it doesn't just drop to 0. Technically, the model we built, it goes below 0. It goes to negative infinity. Is it possible for you to have negative population? No, right? Does it make sense based with your understanding of just predator-prey in the real world? Would this prey, would the prey just necessarily have blah, 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 blah. Would the prey have uninhibited growth? Maybe, right? Again, where you have to go look at the real world example, figure out, okay, does this solution make sense? But even more so, we made this observation that the predators only eat 10 a day. Do you think that's going to be a good assumption?
No.
Yeah, 10 a day, 300 for a 30-day month, right? Yeah, that's probably not going to happen. If the population of the prey starts to decrease, what's also probably going to happen? Predators are going to decrease because they're not going to be able to eat enough. If there's a lot of prey out there, what do you think is going to happen to the predators? They're going to increase. They're going to, because they're also going to be able to eat more, right? So yeah, we built a model, we got a solution, but does this really fit to our observations out in the real world? No. So that's also another important part of all of this process, right? Construct the model, analyze it, i.e. do your calculus, and then make sure it actually matches up with what you're doing out in the world, right? Or what you see out in the world. So you can break it up into the 3 parts. constructing, analyzing, and then comparing. The analyzing we've talked about for the most part in this course, right? We have this type of differential equation. If it looks like this is what we do, multiplied by an integrating factor. We get the general solution. So now I know what I need to do to get the solution to any particular problem because I just plug it in this form, right? It's a little dry, absolutely, 100% necessary. So one of the skills I want us to start sharpening right now is how to actually construct, right? So let's talk about how we work on constructing these models, because as mathematicians, or even if you're a physicist, right, this is probably one of the things you're going to have to do. Physicists are usually slightly more attuned to this process, this part of the process, because they're the ones actually going out and studying the entire physical system, and they're able to then interpret it into the language, right? They're in that nice little mixture. Whereas we get a little bit stronger handhold when it comes to the analysis, but there's overlap. Never pigeonhole yourself, okay? So whenever you deal with a model, you always have to figure out what is being affected, so what you're trying to predict, and then what your independent variable is. It could be time. Time is an easy one, right? So how the population, P, my dependent variable, changes over time, T. How the temperature of this object, capital T, changes over time, T. But it doesn't have to be that. It could be with respect to space. So maybe instead of thinking of time where you're at in this room, depending on my position, the temperature, my body temperature might change slightly, right? Or I might have a headache on some parts. I'm trying to think of something off the top of my head. I'll just stick with temperature, right? Because if I go up a little bit higher, it's a little bit higher up. Technically, the higher up you are, the colder it is. So is that dependent upon time at all? No. What's my independent variable there?
Height.
Height, position, however you want to refer to. Okay. So I have to identify my independent variables and my dependent variables. After that, I have to make sure I understand my units of measurement, right? When I'm talking about position in this room, what are some units of measurement I could use? Feet, meters, inches, millimeters, if I wanted to, centimeters. I have to choose, right? But it's usually going to be something that makes sense. Just like how with that predator-prey model, you know, we're probably not going to actually be able to accurately describe what's happening minute by minute, but month by month, okay, that's much more reasonable to be doing. Plus, if I'm thinking about data collection and going out into the field, I'm not going to be able to collect data that's actually being recording the populations minute by minute, or really even by day. I'm probably only going to find time to go out once a month. Maybe if I'm really lucky and getting some like big NSF research grants to pay for me to just do only that, maybe once a week, right? But never more often than that. So always try to figure out what your units are. And as I say here, it's arbitrary, but you want to make sure it's appropriate. Okay. After that, figure out what is actually happening in the system, right? Articulate the principles. Now with this, there are kind of three main places that you can go to. Part of the reason why physicists are really good at this is because they study those physical systems. So one place you can go look is physical laws. Newton's law of cooling. Force equals mass times acceleration. What is that? Newton's second law of motion? Yeah, that's what we use to build our falling object model, right? We're not trying to come up with anything creative. We're not trying to come up with any new laws. We're just applying things that are out there. So it can be something based on physical laws. Based on your own experiences. Right? Especially if you're a biologist and you're one of the only few that's studying this particular species, there's not necessarily going to be an established law of how this species reacts. Right? You're going to have to use your observations that you've gained over the course of your research to inform what the model should look like. Right? But the biggest thing It requires familiarity with the world. Yeah, there is an I there. Familiarity. Yeah. And depending on who you are, that last one is either something that's daunting. Do I really want to go and have to study some quantum mechanics so that I can understand what's happening and then figure out how I can model it? Or that's also what makes it interesting, because you can become a jack of all trades. I just have to start looking in, learn enough about this area so I can build a model, right? I don't have to be an expert. I just need to know enough to get the said model. Okay. But once you have an idea of what you're modeling, the process, how everything's reacting, then you start transferring that to the mathematics, to your differential equations. So whenever you're trying to build this, you've identified your independent variable, your dependent variable. You want to express this mathematically with those variables. Now here's the thing. This is definitely much easier said than done. So for example, when we were talking about predator preys, we know there's probably going to be some interaction, because if the population of the prey goes up, the population of the predator goes up, right? If the population of the prey goes down, the population of the predator goes down. There could also be, maybe a disease comes through the predator population that wipes it out, has nothing to do with the prey. So if the predators go down from something else, then prey should go up as well. So I have to figure out how to talk about mathematically talking about interactions between things, which is hard. There are some recognized simple ways to do it, which we might get to one, or actually I might take time, since I got screwed over with the biology seminar. I might tell you all the summer research program I'm going to try to do. Anyway, point is, easier said than done. Okay. And then it often requires the introduction of physical constants or other parameters. I'm not going to have enough room, am I? And then lastly, once you have your model, you want to make sure that your dimensions are correct. All right, you've gone through this process, you've built it mathematically, you have this equation, this differential equation. Okay, you want to make sure that it's the valid one. And really what's happening here is I don't want to accidentally mix up, one variable is with respect to days, and then another variable is with respect to months. Okay. So this is what I mean by check dimensions, which really just means check your units. So we can go to that following object equation that we built. Right? What did M represent? Mass of the object. That's one of your physical constants. dV over dt, what does that represent? So derivative is the mathematical definition. So you're not wrong. For what this is describing, it's the change in what? V, and V is representing velocity. So change in velocity over time. So how my velocity is changing over time, we got that from Newton's law of pulling it. Newton's second law, force equals mass times acceleration. We understand that acceleration is the derivative of velocity. That's how we get the dV over dt term. And because force has got to be equal, that force has got to be the force from gravity. What is G? Gravity. Anyone remember what the value is? 9.8, making that a what? Constant. So you get a physical constant, right? Times the mass of your object. And then we're subtracting from it gamma times V. What did that represent?
What is
The gamma times V, what did that represent? So you get the force from falling,
What resistance?
wind resistance, air resistance in particular, right? The only reason you want to be careful with that is because wind usually infers that the air is moving in some direction or not. We're just assuming air is still, whoops, I did it then. Air is still, and all you're doing is falling down. Okay. So what were our units? Is the big thing for all of this. Yeah, so one mass, we just said to be in kilograms. So my mass was in kilograms. Velocity was meters per second, and then I'm taking it per second again. My change in velocity over time. Velocity is meters per second. My over time is in seconds. I don't know why I'm getting hiccups. All right. Acceleration due to gravity. Meters per second squared. Acceleration is meters per second squared. Times my mass, which we measured in kilograms, minus, anyone happen to remember what the units were for the air resistance coefficient? It was kilograms per second. I don't know how no one remembered that. It's obvious, right? And then velocity is meters per second. So this is just how all the units are being combined together. And if this is a well-built model, the dimensions, i.e. the units, should match up. So on this left-hand side, I have a meters per second divided by second. That becomes meters per second squared. I multiply it by kilograms. Get kilograms times meters per second squared. On this right-hand side, meters per second squared and multiply it by kilograms, that entire unit becomes what? Kilograms times meters per second squared minus kilograms per second times meters per second, which also becomes same thing, kilogram meters per second squared. If I take kilogram meters per second squared and I subtract another value of the same units, overall, it's going to be something that is kilogram meters per second squared. So my dimensions do match up here. I know this is a well-built model. Well, actually, I don't want to say well-built. There's no issues dimensionally, right? I'm not accidentally mixing up meters and feet, for example, or seconds and minutes. Also, just a fun little trick I've never talked about before. That's how we also determine kind of what that gamma, the units are for that gamma coefficient. Also, what makes sense. Make sure it makes sense. I probably didn't know what it was before. So if this was unknown and I kind of just say, okay, kilogram meters per second squared, kilogram meters per second squared, then for this to be a well-dimensioned model, I also need what to appear here? Kilogram meters per second squared. I already have meters per second. So I need a kilogram on top and a second on bottom. That constant needs to have the units kilograms per second. That's one way you can come figure out. And that's also how you're able to understand in physics how you can, let's see, hold on. Don't want to get too far out of my purview. So it's a way to mathematically confirm what the units of a constant should be based on your observations or in correspondence with your observations. Right? The air resistance that you're feeling should be somewhat proportional to your mass. And depending on how long you're falling, how far it's or how much it's affecting you. I don't want to go too far into dissecting it because that's about as much as I can get. Okay, but that is one way you can go about checking what things are, as long as you are satisfied that your model is set up correctly. But the point is, for us in differential equations, just make sure dimensions match up, i.e. make sure units match up. If units are matching up, then you should not even be worrying about analyzing the model to begin with. All right. After we construct the model, what will we do next? We're going to analyze, right? Analyzing can have a couple different ways or a couple different approaches. So normally we want to try to find the solution, right? We have a differential equation. If I can find a function that's going to tell me exactly how the object's going to be falling or how exactly the population of the prey is going to be increasing or how exactly the temperature of the object in a room is going to be decreasing over time, that's preferable. Okay. If it's not possible, these models are still useful. Okay. What was some of the things that we did at the very beginning of the semester that still gave us an idea of what the solution should be looking like? So that is the finding solution part. General solution is a solution, but good guess. These equations require derivatives. Derivatives in mathematics are the what of the tangent lines? Slopes. So using those differential equations, we built something called the what? Slope fields or direction fields, right? Even if I can't get the exact solution, I can still look to things like the direction fields or slope fields to get an idea of how the solution should be behaving, right? Should I see my slopes just keep increasing, decreasing? Do I see them going to a specific line, value, whatever? So direction fields. Also called slope fields. And there is another thing that we're able to find without even knowing the solution. I could find a particular value for the solution. What do we call that value? There were 3 classifications for it. Yeah, stable, unstable, asymptotically stable. What do we call those values? Equilibrium values, right? Is there a place that I'm either shooting away from or going towards? And that's usually good enough, right? If I'm modeling a population, I don't necessarily care what the exact value of the population should be 2 months from now. I care more about over a year. Is the population going to be going up, down, staying about the same? Is there just going to be this nice up and down? Am I actually seeing it crashing and burning? So then I need to intervene in some way to make sure that doesn't happen. That's what we care about more often than not. So even though solutions might be a wonderful thing to have, especially for mathematicians, right? That's the gold standard. It's not always needed. Okay. And the reason why you can't get solutions sometimes is because that model may be complicated. All right. How you kind of take those models that are complicated, there's a couple different ways, a couple different approaches. I just have 3 for you. One of them, simplify it by turning something into a constant. Okay. Take a parameter that varies. and turn it into a constant. For example, with the predator-prey models, probably the population of the prey would be increasing and decreasing over time, and thus how much it's eating would increase and decrease over time. But did we assume that how much the predators were eating would increase or decrease or vary over time? No. We took something that would change, made it constant. Making it constant was giving us the ability to then solve it. Okay, so another way, I don't want to do that. Well, I put it here. This is a semi-advanced technique. To approximate a nonlinear equation with a linear equation. I have in my lecture notes to say the difference between nonlinear and linear, but really for what we get in this class, there's not going to be a difference. The idea here is the equations that we've seen so far, whether or not it be separable or the original type, it's looking like a linear function with respect to our derivative or our solution. So when we take dy over dt plus p of t times y is equal to g of t. If I consider the thing that's varying my derivative, I have 1 times my derivative plus some number equal to another number. So it kind of looks like the equation of a line. Okay. If I say y is the thing that's fixing, then I have a number times y plus something else equal to something else. And again, that's looking like the equation of a line. If it's a linear function or linear differential equation, usually pretty easy to solve. If it's nonlinear, things get a lot more tricky, because then you're going to do some complicated u substitutions inside, if it's even possible. In fact, there's an equation that I've been trying to find the solution to that I can't right now. This is an example of a nonlinear equation because I don't have just a number times one of my derivatives. That u sub x represents what derivative of the solution u? It's a first derivative. Looking at you people in intermediate calc, especially. Partial with respect to x. Partial derivative with respect to x is u sub x. U sub y is partial derivative with respect to y. And then plus 1, what do you think u sub t is? Partial derivative with respect to time or with respect to t. So this is called the 2D Burgers equation. This is nonlinear because I'm squaring my derivatives here. So it doesn't look like an equation of a line. And it is extremely difficult to solve. That's what a nonlinear equation looks like. Okay. And then the most important thing just with this, the whole idea is simplify. Simplify, simplify, simplify until you can get to something you can work with. Okay. Sometimes you make too many simplifications to where it might not become useful at all. Sometimes they're appropriate, but in any case, the simplifications you make just depend upon your knowledge of the field. What can I say? This is kind of going to be constant. Even if it changes just slightly, I can level it out, make it a constant value, and it's not really going to affect the end result. It's not just knowledge of the subject area. And that is what applied mathematics really is. We can build the models if we need to, sure, awesome. We'll get those skills. It's more so that when we finally have these models, and if they become too complicated, I can make the right simplifications so that they're no longer as complicated. But I need to know what is possible, right? If we're talking about a falling object on Earth, would it make sense to just not consider air resistance at all? No, we know that air resistance is going to affect it. So I don't want to try to simplify or remove that at all. Okay. In fact, just fun fact, I guess, another fun fact, the assumption we made that air resistance is proportional to your velocity is a simplification in and of itself. That's not really actually how air resistance works, because you can have the same mass. So think of a piece of paper rolled up versus laid flat, right? Piece of paper that's flat, if I try to take it here and drop it, it's going to drop very slowly, right? And also it's going to be kind of moving about. If I ball that same piece of paper up and drop it, it's going to be dropping much faster. So it doesn't only just depend upon your mass. What else does it depend on? Shape, right? Did our model account for shape? No. We just assumed that it was a very smooth object. Wasn't going to have to worry about the shape affecting air resistance and drag. Okay. So I think that's it for the last one. So that, because then we get to, yeah, and the last thing, and really the most important thing is compare. Okay. Our goal is to build something that you can always reference later on. So you need to test to make sure what you built is true. Right? I could probably come up with some crazy model, tell you this is a solution, and I'm going to feel happy. I feel like I'm getting a Nobel Prize for what I did, because I just did a bunch of crazy calculus techniques and came up with some brand new stuff. But if that model doesn't even reflect even close to what we see in the real world, it's not a useful model. Right? I need to make sure I'm comparing, going back and testing in some way, shape, or form. Going back to airplanes, I'm trying to help design more efficient airplanes, so we don't have to listen to them as loudly as coming up here, up and down here on this runway. Right? I can create something. I can give the manufacturer some information, but if my model is wrong, I'm going to send them down a path where they're just going to be building bad airplanes. Okay? So you still want to check. The calculus isn't wrong. It's your base assumption, what your model started with that could be wrong. And if your base is wrong, anything you build on top of it is going to be shaky. Okay? It's always this fun little fine line of what is acceptable and what isn't acceptable on assumptions to make. And that just comes with experience in whatever field you're working with. Okay, so right now, what questions do you have for me? All right. So does everyone know what the ECS program is? Yes, no? So in short, it's called the Emerging Caribbean Sciences Program. What it does, there's multiple different aspects of it because it's an umbrella organization for all the different grants that we get to help support undergraduate research and involvement in research here at UVI. It's also one of the reasons why I love UVI. It's why because we do that and we're actively doing it. It is a program where you'll come in for 6 weeks over the summer. You'll work with a faculty member, potentially me, if you're interested, what I'm about to present to you, and do some research in whatever field. Of course, marine science has a bunch of stuff going on too. If you're interested in that, you can go check it out. And it doesn't have to necessarily be, if you're in differential equations and you see this, you like it, doesn't mean it's what you have to do. If you want to go do some bio research, go do it, right? It's an application process. You still have to apply, submit a recommendation letter, or get a recommendation letter for you, okay? But it does come with a stipend. So you do get paid to do this research over the summer. They also have different workshops that you attend 2 days a week. Last summer it was Tuesday and Thursday for the students. So like how to write a CV for if you're going to apply to grad schools or jobs afterwards, how to give talks, various other just kind of professional tips. I cannot remember the breadth. Please don't think the very small amount of information I gave you is all they do. I'm just not remembering everything. There's a lot that they do, okay? Because what, you meet 2 times a week for 6 weeks total, which means you go through 12 sessions like that, and each session is a different topic. So you also get some professional development along with it. So one of the things that I'm wanting to do, where is it? No, not research, spring. Stop share. Actually, I'll keep it in the recording just in case someone wants to look at it later. So this was attempted by a student with a computer science professor in 2020. Last time or from what I remember, and they weren't able to get any conclusive results. So I want to try this again, especially now that we have much more data to use here in the USVI. So I want to see if we can model using something called an SIR model to see if we can end up building it appropriately so then we can use it later on, just in case we come across another strain like Omicron. So we'll know how quickly it should be spreading. And then once you have that, you can enact public health measures early enough. So what is the SIR model? SIR stands for kind of your 3 basic populations when it comes to epidemiology: susceptible population, your infected population, and then your recovered population. Right? When you start out, you probably have a very large susceptible population, maybe 1 or 2 in the affected population, no one in the recovered. And over time, you're going to be transitioning parts of your population. So first thing that happens, and how in a simple way, like I said, to measure interaction mathematically is through multiplication. So I have some interaction between my infected population and my susceptible population, and that rate of interaction I kind of choose, and that's the value beta, that parameter. Okay. So at whatever this is, this rate, that's how I change from the susceptible population to the infected population. But then the infected population is going to be infected for a period of time, and then you recover. So the rate at which the infected population passes into the recovered population, again, I can just consider it some proportion, right? 10%, so 1/10 up, and so on. And then if you're in recovered, you're just in recovered. So we can actually turn this into a set of differential equations again, because we're talking about how you're changing from one population to the other. So I can talk about how you change in the susceptible population. Well, no one's becoming resusceptible. That's just where you start. So if you're changing the population, it's only because you're losing people to the infected population. So if I'm losing, my change is negative. The rate at which I'm changing is based on the interaction between the susceptible and infected population. And again, that beta is really just figuring out how easy it is to switch between, right? Are you putting someone with COVID 2 feet away in a closed room with no airflow, or are they on opposite sides of the room and wearing masks? Right? That would change the value of beta. When you think about your infected population, it depends on how much is coming in from the susceptible population, but then how much you're losing from people who get recovered. So we build a model. That's where you see that beta SI. So it's what's coming in from susceptible minus gamma I, what you're losing to recover. And your recovered population, whoops, that should be a positive. Just gamma I. Okay. This creates what's called a system of linear differential equations. And with this, you can actually model, because we know solutions if you want exact. If not, you can do Euler's method to get good approximations, which is something that we'll talk about in this class for just a single linear function or linear differential equation, not a system. Or you can use other methods to model. Okay, but the overall goal is we need to figure out what is a good value for beta, what is a good value for gamma, based on the population of the USVI. Because where you're at, you know, just, I mean, be honest here, there's a lot of open air, right? A lot of people just leave their windows open 24/7. That's what I've been doing since I've been. Right? That's different versus someone up in Minnesota, where you're probably locked in a room because you're so cold half the time if you try to step 1 foot out. Right? So our population is different, our constants, our coefficients are going to be different. So we want to figure out what that is. And you can find out all the data that you need. COVID reports from the Department of Health are online. So we're going to go compile all that data, take every single spreadsheet, turn it into one massive one. We're going to use some software to fit the model to the data so we can give us the coefficients. And then we compare our model that we get after doing that to a different set of data. Right? There's a process going through it. You're from statistics, you have your building data, and then you have the test data. So that's what I'm wanting to do this summer. So if you're interested at all, there are plenty of other projects out there, and there's awesome projects that are going on. So don't think it's just me only selling you on this one. Go check it out. Go check out the ECS program, apply, right? Worst case, you apply, you get it, you decide you don't want to do it, then you can make that decision later, right? Better to have and not need than need and not have. So I really recommend everyone to apply. The deadline to apply is February 28th, but if you want to make sure you give get someone who will write you a reference letter enough time to do so, you probably want to start thinking about that now. Okay. If you just Google UVI ECS, one of the first links should pull up the program page. All right, that makes me feel better. Now I prepped all of this and felt bad for Levita because she was organizing the session. She had a couple people. We were supposed to have like 5 minutes to talk. And the first 2 people alone took up 25. Yeah, I was a little irritated right before coming into intermediate calc because I didn't get to share mine because we ran out of time. But yeah, so